in this segment, let us very briefly go through Shannon Fano encoding algorithm, specifically for binary, that is Shannon Fano binary encoding algorithm. Right? So, Shannon Fano encoding algorithm is actually used to provide a compact code with minimum redundancy. So, what are the steps for Shannon Fano encoding algorithm? The first step is to arrange the symbols in their decreasing order of probabilities. In their decreasing order of probabilities. That's the first step. The second step is divide the probabilities into two groups so that they are approximately equal. Right? So you may have a number of symbols. You arrange the symbols in decreasing order of their probabilities. The second step is to divide all the symbols into two groups of nearly equal probabilities. Then 3, all the symbols in the first group is assigned 1 and in the second group is assigned 0. Now what does this mean? Let's assume that there are 4 symbols. It has been arranged in their decreasing order of probabilities, right? In their decreasing order, with P1 the highest and P4 the lowest, divided into two groups with nearly equal probabilities. Let us assume that P1 plus P2 is approximately equal to P3 plus P4. We need to assign 1 to the first group and 0 to the next group. Okay? And this process is repeated. Now again divide the first group into two parts of nearly equal probabilities and assign 1 to the first group and 0 to the second group. Divide this into nearly equal probabilities and again assign 1 to the first group and 0 to the second group. So this process is continued till no further division is possible. And then we obtain the code. So the code for S1 would be 1 1. The code for symbol S2 would be 1 0. The code for symbol S3 would be 0 1 and S4 would be 0 0 here in this case. This is just for explanation. So let's take a specific example and see how we can apply Shannon Fano binary encoding algorithm. So consider a problem wherein there are 6 messages. X1, X2, X3, X4, X5 and X6, and their probabilities are X1 is 0.4, probability of X2 is 0.2, probability of X3 is 0.2, of X4 is 0.1, X5 is 0.07 and X6 is 0.03. Now it is to be noted that when you add all the probabilities, it should be equal to 1. The sum of probabilities of all the messages or symbols should be equal to 1. So when we add up all of them, it is equal to 1. So now divide this into two groups of nearly equal probabilities. So let me combine these two and let me combine these 4. When I add these two, it is 0.6. When I add these 4, it is 0.4. Right? So they are nearly equal. So we cannot have 0.5 and 0.5, right? Because you will not get a case where you have 0.5, 0.5. So they are nearly equal. That is 0.6 and 0.4. So 1 is assigned to the first group and 0 is assigned to the second group. Right? So now again divide this group into 2 of nearly equal probabilities. So since there are only 2, probabilities, you can only divide this into 2. So assign 1 for the first group and 0 for the next. Now here, coming to the next group here. Now divide this into 2 parts of nearly equal probabilities. So this is 0.2. When you add these 3 again, you get 0.2. So I have 0.2 here and 0.1, 0.07, 0.03. So how is the division here? So divide this into 2 equal groups. 0.2 becomes one group and these 3 form another group. So assign 1 to the top group and 0 to the lower group. So again divide this into 2 nearly equal probabilities. 0.1, 0.07, 0.03. So of course I need to combine 0.1 as one group, and when you add these 2 it is again 0.1. So I have divided them into 2 nearly equal probabilities. Assign 1 to the top group and 0 to the bottom group. Right? So again divide this into 2 nearly equal probabilities. So this is the only further division which is possible because we are just left with 2. So combine 0.07 and 0.03, assign 1 and assign 0. Right? So what are the codes? The code for x1 is 1, 1. Right? The code for x2 is 1, 0. The code for x3 is 0, 1. The code for x4 is 0, 0, 1. The code for x5 is 0, 0, 0, 1. And the code for x6 is 4 zeros. Okay, so now let us find the length. The length of the code. What is the length of the code? The length of the first code is 2, since we have 2 bits. 2 here, 3, 4 and 4. Right, so we have the length of the bits. So this is the first process here. So now we also would like to find the code efficiency and the redundancy of the code. Right, that is very important. So now the first thing is we need to find the average length. So I will erase this. So we only need the messages and their corresponding probabilities. So what is the average length L? The average length L is nothing but the summation over I, Pi, Li. What does this mean? The average length is nothing but the length of the code into its respective probability. Right? So what is L? L is 0.4 into 2. So the first message has a probability 0.4 and has a code length 2. So therefore probability 0.4 into 2 plus x2, probability is 0.2 into code length is 2 plus 0.2 into 2 plus for x4 it is 0.1 into 3 plus for x5 probability into length 0.07 into 4 plus 0.03 into 4. Right? So this is the average length. So when you sum up all, you get 2.3 minutes per message symbol. Right? So binary units per message symbol. Right? So now to find the efficiency, we also need to find the entropy H of S is. Now what is entropy H of S? The entropy H of S is summation over I, Pi log 2 base 2 1 by Pi. Right? Probability into log 2 base 2 1 by probability. So what do we have here? So for the first case we have 0.4 log 2 base 2 1 by 0.4 plus 0.2 into log 2 base 2 1 by 0.2. Right? So I have two of them. So I write 2 into plus. Next I have 0.1 log 2 base 2 1 by 0.1 plus 0.07 log 2 base 2 1 by 0.07 plus 0.03 log 2 base 2 1 by 0.03. Right? So now the question is, how do we find log 2 base 2 1 by 0.4? So in your scientific calculator you will have log 2 base 10 calculation and ln, which is log 2 base e. So to find log 1 by 0.4 to base 2, I can either use log or ln. Right? So one method is, what you do is you do log 1 by 0.4 to base 10 divided by log 2 to base 10. Okay? Or you can do ln, that's log 2 base e 1 by 0.4 divided by natural log 2. Okay? So then you would get log 1 by 4 to base 2. So you would be doing it for all the cases. Okay? So when you do the calculations, finally you would get H of S to be equal to 2.209 bits per message symbol. Right? So we have got the average length as 2.3 binary units per message symbol and H of S, the entropy, as 2.209 bits per message symbol. So now we need to find the efficiency. So how do we find the efficiency? The efficiency, the code efficiency is H of S by the average length L. So H of S is 2.209 divided by 2.3. So we get it as 0.9604, or the efficiency is 96.04%. Right? So please make sure that you do the calculations using the calculator and you get these values. Right? So the common mistake is to go wrong in these calculations while operating the calculator. So make sure that you do the calculations correctly using your calculator and you get the correct values. So how do we find the redundancy? The redundancy is nothing but 1 minus 0.9604, which is 0.0396, or it is 3.96%. Right? So the code redundancy is 3.96% and the code efficiency is 96.04%. Right? So this is how we have obtained the code for the messages x1 to x6 using Shannon Fano encoding algorithm. Now in the next case, let us take, so there are two symbols S1 and S2 with their probabilities given by 3 by 4 and 1 by 4. That is the problem. We need to find the code efficiency and redundancy, and also find the code efficiency and redundancy of its second extension. Okay, so first let us try to find the code efficiency and redundancy of S1 and S2, and then find the efficiency of its second extension. So now we have already listed the messages or symbols in their decreasing order of probabilities. Divide this into two groups of nearly equal probabilities. So this is the only division. Assign 1 to the top group, 0 to the bottom group. So what is the code? The code is nothing but 1 and 0. And what is the length? The length is 1. So the average length L, the average length L is summation over I. It is Pi into Li. So probability into its length. So therefore it is 3 by 4 probability into 1 plus 1 by 4 into 1. So we get 1 binary units per message symbol, right, or minutes per message symbol, right? Okay, so this is the average length L. So let's try to find the entropy. The entropy H of S is summation over I, Pi log to base 2 1 by Pi. Right? So I've already explained how we need to find log to base 2 value. So it is 3 by 4 log to base 2 1 by 3 by 4 plus 1 by 4 log to base 2 1 by 4, right? So therefore we get 0.8113 bits per message symbol. Right? So make sure that the calculations are done correctly using the calculator, and please do not forget to write the units. So now to find the code efficiency. The code efficiency of the first extension, I'll write 1. So the code efficiency of the first extension is nothing but H of S by L, which is 0.8113 by 1, which is nothing but 81.13%. Right? So we realize that the efficiency is pretty low for the first extension, right? For S1 and S2. So now let us try to find the efficiency for the second extension. So how do we find the second extension? The second extension is obtained by multiplying the symbols. So I have S1 and S2, two symbols. So the possible variations which I could get for the second extension is multiply S1 with S1, multiply S1 with S2, S2 with S1, S2 with S2. Right? So these are the second extensions. So now what are its corresponding probabilities? So the probability of S1 is 3 by 4. So 3 by 4 into 3 by 4, I get 9 by 16. 3 by 4 into 1 by 4, it is 3 by 16. Again 3 by 4 into 1 by 4 is 3 by 16. And 1 by 4 into 1 by 4, I get 1 by 16. Now again, when we sum up all the probabilities, it should be equal to 1, right? So when you add up the numerator, 9 plus 3 plus 3 plus 1, you get 16 by 16, which is 1. So therefore the sum of all the probabilities is definitely equal to 1. So now, considering this, again follow the same procedure. Divide the probabilities into two nearly equal halves. Assign 1 and 0 to the bottom group. Again divide this into two nearly equal halves. So I would get 3 by 16 3 by 16 and 1 by 16. So divide this again into two nearly equal halves. So I get 1 and 0. Again divide this into two equal halves. So you get 3 by 16, it's the top group, and 1 by 16, the bottom group, we get 1 and 0. So now let me list out the code and the code length. The code for the first one, S1 is 1 with the length 1. The code for the next one is 0, 1, length is 2. The next one is 0, 0, 1, length is 3. And for the last one is 0, 0, 0, it is 3 again. Right? So now let's try to find the average length. The average length is again summation Pi Li. So it is probability 9 by 16 into 1 plus 3 by 16 into 2 plus 3 by 16 into 3 plus 1 by 16 into 3. Right? So we get 1.6875. So we get 1.6875 binary units per message symbol. Right, 1 point. So please calculate and check the answer. So now the entropy for the second extension. Now we know that the entropy for the second extension is just 2 into the entropy of the first extension. That is by property. So h of s square is nothing but twice h of s. Else you can find out the entropy by individual calculation by calculating using these standard formula. But we know that the entropy of the second extension is twice h of s. So it is just 2 into 0.8113, which is 1.6226 bits per message symbol. Right? So now how do we find the efficiency? The efficiency of the code for the second extension is the entropy of the second extension divided by the length L. So it is 1.6226 divided by 1.6875. So we approximately get 96.15%. So we get 0.9615 or 96.15%. So here we observe that when we go in for the second extension, the code efficiency dramatically increases. So in the previous case, the code efficiency was just 81.13%, but now here in the second extension, the code efficiency has remarkably increased to 96.15%. So this is how we can do Shannon Fano or use Shannon Fano encoding algorithm to get a compact code for the given symbols or messages.